even in the solar system, I would not be surprised if we find microbes on Mars or on some of the moons of Jupiter or Saturn where there's liquid water.
Like Europa.
Yeah. And the reason is, if you think about, the reason I think that, and it's a guess, is because if you look at the history of life on Earth, then, so Earth formed and it was just there was no life, it was a ball of rock. And almost as soon as it cooled down, we see evidence of life. So certainly 3.8 billion years ago, possibly even further back than that, we see evidence of life on Earth. So somewhere along the line, geochemistry, active geochemistry became biochemistry on Earth. And we have some idea, that if you get gradients of temperature and acid and alkaline and the conditions that are naturally present on the surface of oceans, then complex carbon chemistry spontaneously happens. So we know that life, almost certainly we know that life began on Earth. I mean, the other option is it came from space or something like that, but it probably didn't. Right? It probably began on Earth.
That it's possible that octopi had come from somewhere else. Some frozen eggs had actually come from somewhere else and landed on Earth. And these were like legitimate scientists that were contemplating, not morons.
I don't think...
Have you seen this?
No, I didn't. But I mean, I think it's unlikely. So panspermia doesn't have to be unlikely.
Right.
I mean, for example, you might have seen the other day we found an Earth rock on the moon.
Yes.
Right. Well, it's back on Earth now because the Apollo astronauts brought it back, didn't they? It was 4 billion years old or something like that.
One of the oldest rocks ever found.
Yeah.
Right.
So we know that material gets transferred between planets. And so it's not inconceivable that microbes could survive that journey. Right? We know that microbes can survive in space, for example. So that isn't mad. It's probably unlikely, but it's not mad. But with the octopus, I hadn't heard that. But the thing is that the octopus is still extremely similar biologically to us. I mean, the differences are negligible.
Yeah.
So it's still got the same energy system with a single ATP and DNA and all that stuff. It's all very, very similar. So a thing called dark matter.
Yes.
So we look out into the universe and we see that there's a lot of stuff there that's interacting gravitationally, but is not interacting strongly with the matter out of which we are made and the stars are made. So it's almost certain that that's some form of particle, that fits beautifully. And we see lots of different observations of the way galaxies rotate and interact, and even that oldest light in the universe, the so-called cosmic microwave background radiation, we see the signature of that stuff in that light as well. So we think that there's some other particle out there. And to be honest, we thought we would have detected it, I think, at LHC. We have lots of theories called supersymmetric theories that make predictions for all sorts of different particles that would interact weakly with normal matter. And I think it's broadly seen as a surprise that we haven't seen them at LHC. So that just may well mean that either they're a bit too massive, so we need more energy to make them, and we just haven't quite got enough, or we're not making enough of them often enough to see them, which is one of the reasons we're upgrading the LHC. So we also look for them, by the way, directly. So we have experiments under mountains. We bury them under mountains so the cosmic rays from space don't interfere with them. And we're looking for the rare occasions when these dark matter particles bump into the particles of matter in the detector. So because the idea would be this room's full of them. I mean, the galaxy's swimming with dark matter as far as we can tell, but it interacts very weakly with this matter. The archetypal particle that's everywhere that doesn't interact strongly is a neutrino. So we do know about neutrinos, we've detected those. And there are something like 60 billion per centimetre squared per second passing through your head now from the sun. So they get made in nuclear reactions in the sun. But they go straight through your head and then actually straight through the Earth, pretty much. Occasionally one of them bumps into something. And we can detect those because there are so many of them going through. But we only detect, I don't know, 1 or 2 a day.
And the idea is that dark matter encompasses an enormous percentage of the universe.
Yes, it's 5 times as much matter as dark matter than is normal matter. And the number is 25% of the universe. So roughly speaking, about 5% of the universe is normal matter, stars and gas.
25% is dark matter.
Yeah, so 5 is normal matter, about 25 is dark matter, and about 70 is dark energy.
That's the other thing I was
the other
ask
thing
you about.
Yeah.
Yeah. So what the hell's that?
Don't know. It's a supernova. The light from supernova explosions, which are so bright that you can see them, hundreds of millions, billions of light years away. And he noticed that if you look at the data, the light is stretched in the wrong way. So we look at the stretch of light as it travels across the universe, and the universe is expanding. It stretches the light, so it changes the colour. And he noticed that there was a discrepancy, which said that the expansion rate is speeding up. It's been speeding up for, I think something like 7 billion years or so. It's been speeding up. But the best way to explain the universe, the properties that we see, is that it's very much bigger than the piece we can see. So, for example, we measure space to be what's called flat. I don't even have to say what's called flat. It is flat. So if you imagine slices of space, let's imagine slices of them at different times. So you just slice the universe and say there's a big sheet. It's like this table.
Okay, like a table.
There's a sheet of space, and there's another sheet, another sheet. And it can have a geometry, right? It can be flat like a tabletop, or it could be curved like a sphere, or it could be curved in the opposite direction, sort of like a saddle or a bowl. And we can measure that. And when we measure it, we see it's absolutely flat. And that's a very unusual thing for it to be like. It requires, because what Einstein's theory says is that the shape of space, that the curvature of space is determined by the stuff that's in it. That's basically Einstein's theory of general relativity. Put stuff in space and it curves it and bends it and warps it and stretches it and so on. And what we find is that there's precisely the right amount of stuff in the universe to have a completely flat universe. And the explanation, the most favoured explanation for that, is the universe is way bigger than the piece we can see. And so it's like looking at a piece of the Earth. If you look at a little 1 mile square of the Earth, right, then it's flat, right? You have to look at big distances to kind of order the radius of the Earth, or not, bigger than 1 kilometre anyway, or 1 mile, to see that actually you're on a curved surface. And that's one of the ideas about the universe and why it appears to be the way that it is, because it's way, way bigger. So we're just looking at a little piece, and that's why it looks flat. And that's, if you look at the Andromeda Galaxy, which we can see with the naked eye here in LA, you can see that. It's the most distant object you can see with the naked eye, and it's about 2 million light years away or so, which means the light took 2 million years to get to us. So it's a long way away, but it's very big. So as you look further out into the universe to more and more distant galaxies, you're looking further back in time, because you look at something that's 1 billion light years away, then the light took 1 billion years to get to us. So you see it as it was 1 billion years in the past. And we can actually look so far out that we can see almost back to 13.8 billion years ago, which is very close to the Big Bang. So we can look to light that began its journey before there were galaxies. And that's the oldest light in the universe.